Let's now get back to our example and apply the principle of information gain and entropy on our data set. So initially, we start with a root that has 8 positive and 6 negative examples. The corresponding entropy for 8 and 6 is 0.985, which corresponds roughly to some value very close to the top of the entropy. Why? Because the proportion of positive example is actually almost equal to the proportion of negative examples. So the entropy for at the root level is 0.985. Then we're going to pick one of the features to work with. Suppose we pick highest degree that has as possible values bachelor's, master's, and PhD. If we split by each of these values, we get an entropy of 0.97 on the left node, 0.722, and 0.811. So the node, for example, in the middle corresponds to the entropy of having 4 positive examples and 1 negative example, which lowers the entropy at this node. So overall, we see that we're going from 0.985 into a 0.97 for this node, 0.722 for this node, and 0.811 for this node. Now that we have calculated the entropy at each of the nodes, we're going to see how much gain we obtain by splitting the root based on this feature. So the gain at the root node based on the feature highest degree will be equal to the entropy at the root, right, minus the entropy at each of the children, right, each of which is actually weighted by the proportion of number of examples divided by the total number of examples. So for the first node, for example, we have 5 examples among the 14 examples initially. This gives us a gain of 0.149, which corresponds to how much we gain if we split by this feature. So we'll do a similar process for the feature work experience that splits based on the 3 values of web dev, mobile dev, and UX design. So basically, the entropy at the root is the same, right? We always have 8 positive versus 6 negative at the top. If we split that work experience, the node that is on the right left will have an entropy of 0.81. The nodes in the middle would have an entropy of 0.65, and the nodes on the right will have an entropy of 1. So it's clear that in the node on the right that actually what we are getting is really we are at the maximum of the entropy value. Why? Because we have 2 positive and 2 negative, which means that our proportion of plus is equal to our proportions of negative examples. Likewise, we're going to calculate the gain of gain at the level at the root level and pick in work experience, which will be equal in this case as 0.189. We do the same thing for the feature favorite language. We obtain a gain of 0.258. And finally, we do a similar splitting by need work visa, that is either true or false, right? In which case, we're going to obtain an entropy of 0.985 or 0.985 if the need for work visa is equal to false. In this case, observe that the gain is equal to 0, which means that we gain nothing by picking this feature. So it's good news that there was no decision made on hiring people based on their need for work visa or not. Okay, so this figure here summarizes all what we have done so far. By picking for each of the values, we obtain a gain, and we're going to compare these gains in order to make our decision about which features to pick next. All right, so we summarize these gains into this table. So we have the feature and the information gain obtained. So we see that the need for work visa was 0 because we didn't gain anything by splitting by this feature. And it appears that we are having the maximum of gain if we pick a favorite language. So at the first split, starting from the root, we choose the attribute favorite language that has the maximum gain possible. Then we'll start the same process at each of the children nodes of favorite language. So you might have noticed that the data we have been dealing so far with decision trees is purely categorical, which is one of the main strengths of this decision trees. It works great for categorical data. What if your data is numerical, such as this example in which we have in the same example, the number of paper published, the year of work, the grade point average, and the need for work visa or not. So we have 3 features that are purely numerical, and we need to do something with that when we feed that to the decision tree. So the way it works is either you first start by discretizing your values. For example, you could put some intervals instead of the value. So this 3.20 could be replaced by something like between 3 and 3.5, right? So you could discretize this way, or you could also let the algorithm handle it. And the way the algorithm handles it in decision trees is by putting kind of cut points. These cut points are basically the values in the table, and you would count. It would count the proportions of positive and proportions of negative after and before the cut point. So you could calculate the entropy based on different cutoff points on the scale of this feature. So in the past lecture, we spoke about overfitting the data. This is one of the main problem that you need to take care of when you build a model. You want to build a model that does not overfit the data. In other words, that have a good generalization capability. All right. So in the case of decision trees, decision trees are not an exception, and overfitting can happen very easily simply by developing the biggest possible tree, which means that you're going to fit your data perfectly. You're going to learn every single data object or data instance by heart. Okay, so if we illustrate that with a graph, so suppose you're putting the size of the tree in the x-axis, right? Size of the tree. It could be simply the number of nodes in the tree, right? And you put on the y-axis the accuracy of your decision tree, right? I'm going to plot what would roughly the accuracy on the training set look like. So if you're starting, suppose that the accuracy is going, actually the accuracy shouldn't exceed 1, so you're going to be 100% accurate on classifying your example if you learn the best possible tree, which is the biggest. Suppose we have our data split into 10, 20, 30, 50, 60, up till 100 nodes, right? 100 nodes would be the largest possible tree you could build with this data. So if you observe the behavior of the accuracy as you increase the number of nodes, you would see something that would really go high this way, which means that you're going to get 100% accuracy on your training data. However, if you apply this model as you go on your test set, you're going to observe that your accuracy will probably be okay at the beginning. Generally, you could expect like 10% drop, but then it will go down as you actually are overfitting the data because you are going to stick with data too much. So remember this very specific description of the tree that doesn't let any other tree go through. So your accuracy on the test set will be going down, so this is the test, while you observe that actually you are doing better and better on the training data. And here you could see that actually this gap in accuracy is simply due to the fact that your decision tree is really specific to the data that you have in your training set. To avoid this problem from happening, we are going to deploy what we call pruning strategies. So to get a suitable tree size and avoid overfitting, what we can do is, first of all, we could stop growing the tree earlier before it reaches the point where it perfectly classifies all your training examples. So it's difficult to know a priori when to stop, but you could do that and do different tests to see what's going on. A second strategy to prune is to do rule post-pruning, which means that you take your decision tree and you transform it into rules. So remember, you have the root level, and you have one feature. So if the feature is equal to this value, and the second feature is equal to this value, and then the class is 1 or -1 or +1. So you could turn your decision tree into a set of rules and do the simplifications with just simply the rules that you have obtained. Another method to build decision trees invented in the statistics by Leo Breman is the CART method. The CART method adopts the same greedy search top-down algorithm to find a decision tree that matches the data. So except that CART uses binary splits instead of multi-way splits, like in the decision trees we have seen so far, in which each feature is split by all of its modality. In CART, it's just binary splits. And it also uses another index to measure the mix of the classes in the nodes, which is, in this case, instead of entropy, it uses the Gini index. The Gini index is based on also the proportions of positive and negatives, but just put them differently. In this case, the Gini would be 1 minus the proportions of positive examples square minus the proportions of negative points square. Okay, so this is pretty close to the entropy measure. It just doesn't have the log of the proportions. So you could see in this curve that actually the Gini index in blue is pretty close to the entropy index. And two methods perform similarly. Here are now some practical consideration when you use decision trees in your applications. So first of all, consider performing dimensionality reduction beforehand to keep only the most discriminative features, the most important features that are relationship with the label. So we have seen, for example, that the visa status has nothing to do with the decision of hiring an applicant. So it's best to remove it from the beginning and avoid doing the calculations with this feature. So you could imagine if you have 10 or 20 or 30 features of this kind, you gain lots of you have lots of gain just removing them from the beginning. The second one is combine your decision trees. So this is what we call in machine learning using ensemble methods. The decision tree has proven to work very well in many applications. However, it's proven that when you combine them, they work even better. So you could think of something like using random forest, which is a great approach to obtaining the best performance of your decision tree. You could also check this paper that actually provides a meaningful and comprehensive comparison between different machine learning algorithms. The third consideration is to balance your data before training to prevent that the tree will just learn the bias class or the most dominant class. So suppose you have 90% of your data is positive examples, and the rest is negative examples. It's very easy to find a decision tree that would classify 90% of your data as positive. So in this case, you'll have great accuracy, but you'll do poorly on the remaining 10%. In this case, you just need to rebalance the data so as you could do decision trees that can be really affected by this kind of scenario. Okay, so if there is a skewed distribution, just balance it. The way to balance it, you could either use what we call undersampling. So you could, if you have a lot of data, just bring down the majority class. And if you're careful about, you don't have that much data, what you could do is oversample the minority class instead. Okay, so make sure that your data is balanced before you go ahead and run your decision tree. Finally, what are the tree classifiers' pros and cons? So first of all, you have seen that it is very intuitive. It also has very interpretable behavior, which means that by looking at the tree, you know what's going on, what are the features that are deemed to be most predictive of the outcome or the label. It can be turned into rules if the applicant knows Java, and if the applicant has a master, then it is likely to be hired. So you could turn the tree into rules, intelligible rules. It is also very well suited for categorical data. It's simple to build, and it doesn't need to scale the data, keep it just as it is, okay? But however, you need to balance it. The cons of tree classifier is that they are unstable, which means that changing one example in your data may lead to a completely different tree. It's also univariate, which means that splitting the data is done only one attribute at a time, which means that it does not really combine the features, right? It just consider one feature, one vision of one feature at a time. The fourth con is that a choice at some node depends on all the previous choices, because there is this sequence of choice of your features. And finally, you need to balance the data, otherwise this is a problem and you'll get a very biased tree that is just learning one of the classes.